So this will be a webinar about extreme scale high-fidelity CFD using the code Neko. So I'm Niklas Jansson. I'm from KTH, from the HPC center at KTH called PDC. And Neko is one of the codes that are used inside the Euro HPC Center of Excellence SEEK for exascale CFD. So to give a bit of a background, so the idea with this webinar is to showcase where we are with the state of the code. We are about to release 1.0 of the code, so highlight some of the new features that we're adding into it, and also some of the technical features that we might not have talked about in other settings. The second half of the webinar will be more of a tutorial-like thing. We will go through how to set up a case, how to run it, but it will not be a full tutorial because that will take more than the allocated hour for this. So see this more as a way of getting pointers to further reading or examples so that you can try this out yourself. And also it's a great start because there will be some upcoming tutorial and training material videos produced in conjunction with the 1.0 release of Neko as well. So to give a bit more background and motivation, we are doing CFD, and why are we doing this and why it's important? Because there's a lot of energy used in the world overcoming this turbulent friction, and to create better airplanes, better cars, we need to have very detailed simulation, so-called wall resolve simulation. And for that, you need to do a large amount of compute. This has been highlighted by Trace, it has been highlighted by NASA. And the interesting thing with CFD is that compared to other scientific fields, we are not limited by the size of the system. So we can still add a lot of grid points and we get more and more science out of our simulations. And this is why CFD is one of the areas with a clear need and a great potential to reach exascale. And this is where SEEK enters, because exascale is going to be a difficult beast to tackle. And the idea with SEEK is to address this extreme scale computing challenge to enable the use of accurate and cost-efficient high-fidelity CFD simulations at exascale. And the goal here, the concrete goals, is to implement exascalated workflows addressing grand challenge scientific problems. That means going from the idea, creating initial data, running simulation, and taking care of the huge amount of output data that you get. But to enable to run this on new machines that are coming or already on the floor, we need to develop new or even improve the current algorithms we have so that we can exploit these new systems, for example, GPUs or new network or hardware with not the traditional double precision floating point that we might be used to. Another important aspect is also to improve the energy efficiency of our simulations, because energy is a big concern when we're rolling in these bigger and bigger systems. And all this development is done in a couple of lighthouse cases. And the lighthouse cases are then paired together with what we call a lighthouse code. And these cases are then selected to be relevant for both academia and industry. And the project itself has 8 partners across Europe, and the partners are bringing in either a lighthouse case, a lighthouse code, or competence in various parts of the algorithmic toolchain, from numerics down to the computer science part as well. And then we work together to create these demonstrative lighthouse cases at the end of the project. And so this is a short overview of the project, getting more into the concept and challenges where we would like to see running at scale on this big machine. You can look at this in 2 ways. One way is that you have a big machine and then you just inflate your problem so it becomes unreasonably large. And that is always easy to run, or easy, but it's always possible to run that efficiently on a big machine if the problem is big enough, but the downside is it will take a large amount of time. A more interesting way, I would say, is actually to, and also probably the most viable way, is to actually instead addressing the algorithms and improve them significantly such that they can run more efficiently using what we have right now. So think of taking one of the largest meshes you can possibly find, and then instead of just creating that 10 times larger, scale that up in a 10 times larger system with the same sustained efficiency. So that will be faster as well. So in the end, this will become a strong scaling exercise, and that's sort of the true challenge on running on the next scale machine. So to illustrate this a bit further, back in days we were running finite volume simulation, LES simulations of full cars on the entire K computer. That required around 100 billion grid points to run efficiently. K computer, the red machine up there in the right corner, that was north of 500,000 cores, 10 petaflop. And if you do any flop-to-flop comparison, that is now half a rack of GPUs in our machine Dardell at KTH. And if you want to extrapolate this, of course, then you will get a bit of a nightmare thinking what kind of problem you need to do using similar methods to run on the full 380 petaflop Lumi, and even now going forward to the full Jupyter that is close to an exaflop. So the solution here, and also illustrate what I tried to make in the beginning, that we need to improve our methods. We cannot use low order finite volume. We should go to high order methods to give us good numerical properties, but they're also very well suited for the modern hardware like accelerators, but also modern CPUs that we have now in the current machines. So, but of course, there's no free lunch. The plot down there to the right, it's showing a kernel from a benchmark suite from ECP, using one of the codes in Seek. And the red line there is actually performance on a CPU. And the x-axis there is the number of elements. So the CPU is hovering around 1 teraflop, regardless of the input problem size. While the green line, now this happens to be an NVIDIA A100, we see that when the problems gets larger and larger, the accelerator will become very happy and produce faster and faster, running the code faster and faster. But this sort of goes against what I said in the beginning, that sort of speaks for doing these artificially inflated problems. So the real challenge is to actually be on the left side where the GPU is sad, and then tune your method such that these will be running very fast as well. A bit more theory. High order in this setting is spectral element. So that is normal finite elements, but with high order basis functions. So nth order Legendre Lagrange polynomials and well-suited quadrature points, then you can express your local solution per element as a fast tensor product formulation. And it has been known back from the 80s. It's actually working very well on CPUs, because instead of having a low byte to flop ratio, you can now move to level 3 BLAS and do more like matrix operations, which, if you follow development in GPUs, that's more exactly what is now driving AI as well with this tensor cores as well. The downside is, if you're coming from the finite element world, is that you cannot assemble these matrices. They're becoming too expensive. You really got a lot of dense blocks in them. So the key for achieving good performance here is to actually use what's called a matrix-free method, that you never assemble them. You sort of keep these unassembled local element matrices sort of as an illusion on the diagonal of your matrix, and then your function will be replicated with extra data on the element boundaries here as well. And that's what is called this UL in this formulation. With this, you can reduce the operation count to the n to 4 instead of n to 6. But since we want to have continuous functions across the elements, we need to do what's called a gather-scatter operation. And this is done by having a gather scatter matrix. A Q transpose is the gather and Q is the scatter. And then you can move between the replicated UL formulation and the unique U formulation without duplicated points by just multiplying. For example, UL, if you multiply from the left with Q transpose, then you get the unique representation without duplicate. But of course, if you cannot form A, you cannot form Q either. But it turns out, when you do work this out, is that you only need action Q transpose inside Krylov solvers. And Q transpose turns out to be just nearest neighbor point-to-point exchange in these red and green dots that you see here in the lower right. And these are sort of the core concepts then getting into what we refer to as Neko, which is this portable spectral elements framework. It is a high-order spectral element flow solver or framework. It does mainly incompressible Navier-Stokes. We also have a compressible solver in the making that will not be ready for the release, but it will soon be released as well as part of the framework. So the key focus for us is to optimize these small tensor products, optimize this gather-scatter kernel. We have written this maybe a bit unusual in 2025, but we're doing it in modern object-oriented Fortran. The reason for that is because we had a lot of Fortran code from our previous usage of NEC 5000 at KTH. And the cost of rewriting that's of course negligible compared to the verification and validation cost of all that code in a new language. So we felt that it was actually less expensive going with the Fortran 2008. But we need to support accelerators, and that is done via a hardware backend that we have a device abstraction layer so that you can actually run Neko on devices supporting CUDA, HIP, and OpenCL directly from Fortran via our own device abstraction layer. In situ, in transit interfaces are in place as well, so you can do visualization and post-processing. And then it's not part of Neko per se, but it's in the same place in the repository on GitHub and the Extreme Flow organization there. It's a spectral element post-processing suite written in Python called PySubTools, which works both for Neko, NecRS, and Neko 5000 as well. So just doing a bit of commercial for this nice suite of post-processing tools as well. So recent developments that are now scheduled for 1.0. So we are getting turbulence modeling in. We have a couple of LES models. We do have immerse boundaries based on Brinkman and some inverse distance. And we also have an API final in the code as well, such that users easily can interact with Neko from various entry points. So if you look at the top to the right, all this work was actually part of running on more or less the full Lumi for our Gordon Bell run. We were a finalist 2023, and the code shows excellent scaling up to 80% of that machine back in 2023. It's not only due to all the good code, it's also due to that we tried to make this into an exercise in modern software engineering. So we're running unit testing, verification, validation suites like Reframe, also Cube, and we are getting things ready to get it into what's called Benchmark as well. And we are also trying to make it easy for developers and users to install it using tools like SPAC. So Neko is in SPAC, so you can always install it easily with a SPAC install Neko and then all the variants depending on the backend that you want to run on. So if you want to know more, after the webinar, we have a very easy website down in the lower left corner. It's easy to remember. It's neko.cft that will bring you to the homepage of Neko. And from there, you can access documentation and also get to the GitHub repository. So highlighting some of the technical stuff behind the scenes that might be interesting for people that have not listened to Neko before going to the tutorial. First of all, we have the device abstraction layer. And this is really our way of writing an interface to the various accelerator implementation that we have via C interfaces in Fortran. So you can easily allocate memory inside Fortran by calling a Fortran function called device alloc, for example. And that's sort of you hide all different memory management behind this interface. So either you go down into CUDA malloc, HIP malloc, or CL create buffer, depending on the backend that you compiled Neko with. We also have a couple of memory management. So we can associate host pointers with device pointers. So where you are in your code, you can easily look up if this pointer or this array is on the GPU or the host and vice versa. So all these things like memcopy, memory management, that is done from the Fortran side, but launching the actual kernels are done via sort of an object hierarchy from Fortran. So we go into a C interface, into wrapper function for each support accelerator backend. And from that wrapper function that is typically in C or C++, we are launching templated CUDA HIP kernels, or if you're using OpenCL, it's going to be a interesting, peculiarly pre-processed macro mess just to get all these runtime parameters as constant. For example, the polynomial order, which is key to get good performance in these kernels. An important thing is that depending on your polynomial order, how these kernels are written can give you a large difference in performance. So the first time you are executing, for example, A times X, a matrix vector product, then the Neko will run a test to see which kind of kernel strategy is the best, and then pick that one until when next time you run, invoke that kernel with the same polynomial order. And this is important because inside Neko, we will see later on we talk about solvers. We are using multi-bit methods where we need a sweep of different polynomial orders so that you actually need to, and you can, of course, then switch the strategy for the different polynomial orders. That is done automatically. Other thing that's important to make this fly is, of course, to get a scatter. And just an update here on what we support. Traditionally, we have only done MPI in Neko for the guided scatter operations, but we have recently managed to get a prototype for NVSHMEM into the code that will be part of the Neko 1.0 release, but it's more in a beta stage there. We also have, and if you don't know what SHMEM is what the figure is showing down to the right, that we're actually creating a symmetric heap across all the processing elements, all the GPUs in this case, And then the GPUs can read and write via put and get operation into the different GPUs memory without doing the message passing thing of doing handshaking and these kind of things. So it's an interesting way. It's an old technology from CPUs, but now this is part of the GPU stack from NVIDIA. The last two here, the nickel and RICkel, these are typically the collective communication libraries. So most people are using them for doing reductions, for example. And Neko can be configured to use them for reductions. But the gather scatter also uses the new point-to-point interfaces that are in the nickel and RICkel library as well. And that's part of the release that is soon to be out. Something about the optimizations we do here to understand a bit what's happening if you try the code. We are trying to overlap communication computation as much as possible, especially for device-aware MPI. So the figure to the right, top right there is part from the LumaG documentation, and one can see that the network is actually going directly into GPU. So if you're not using device-aware MPI here, data will be sloshing back and forth between different memory spaces before they just go out on the network. Another thing we try to minimize, because we're running on big machines, we want to minimize the effect of late arrivals. It might be so that we get a very unlucky node that is on the other end of the machine room. So when we're doing these exchanges for the gather scatter, we don't want to wait for all the communication to be done before we start processing the data. So we're launching the pack operation and also the unpack operation after we receive the data in a stream per neighbor, such that you're always making progress. And if you look at a trace here in the middle, that's why it's going to be like a waterfall of small kernels here that is actually one pack or unpack operation per neighbor. But it could be that in certain configuration, your job has been launched in a certain way, such that it's actually better to not pack, for example, all the data into different streams. Or it might be that it's not favorable to launch a unpack kernel as soon as matches arrive. And again, here we're doing auto runtime tuning at the start of the simulation, so that given your problem, given your job partition that you got, then we determine the best strategy for the data that you will actually be exchanging in this gather scatter. One more thing about SHMEM that makes it a bit interesting down at the bottom is that with SHMEM, we don't need to separate MPI as a communication and computation anymore. So when you're doing MPI with GPUs, you often have to sync the GPUs before you issue the MPI. But with SHMEM, since what is called GPU-initiated communication, you can just scheduling everything onto the accelerator, and both computation and communication will be handled by the accelerator following the scheduling policy that it has, which makes for a much easier way of writing quite scalable kernels and solvers as well. So a bit about the numerical method. Not going too much into detail here, but we have an explicit scheme, so that in each time step we are solving for the incompressible solver now 4 systems, 3 for the momentum, the fluid, so the X, Y, Z velocities. These are quite inexpensive. You don't need such a good precondition for those. But then you have the pressure equation, which is the main source of stiffness for the fluid equation, or for the Navier-Stokes equation. And that's why you need a good solver for the pressure here as well. And that is why we have spent a lot of time developing scalable linear solvers in Neko, looking at communication, which is the main bottleneck in these iterative solvers, basically Krylov solvers, because we cannot communicate across the entire computer room. So you need to minimize what we call horizontal communication, especially reductions. Krylov solvers has a lot of reductions. And to overcome this, we are trying to rework our solvers into what's called pipeline formulation. So we overlap communication with computation. The other kind of communication that we try to minimize is the so-called vertical ones between different levels in memory. And there we have in the past done some graph modeling by doing like a directed DAG, showing computation and the dependencies, and then see if we can recompute because flops are free on devices, or it's better to just load the data from memory as well. And based on this, we are formulating new solvers that is using heavy what's called fused, so kernel fusion. So instead of having what we see here on the right, that we have a lot of small kernels from this trace, we try to fuse them into larger block to make the GPU happy. And we also come up with what we called a coupled formulation. So instead of launching as traditionally one linear solver per X component, so X, Y, Z. We are solving them together in sort of a coupled fashion, so multiple vectors. And then we can, in the spirit of reducing vertical communication, reduce a lot of data that we are loading from the slow GPU memory into the fast memory on the GPU. So currently, the code which is more in the production state, we have the current kernel solvers are the GMRS, and conjugate gradient CG, pipeline CG, pipe CG, and fused CG, which is a CG when a lot of these kernels are already fused. And then for some of these, you have this coupled formulation as well, specifically for the velocity problems. So when it comes to preconditioners, these kernel solvers are not going to fly unless we have good preconditioners. And there we have the classic spectral element preconditioners, additive overlapping Schwartz multigrid, which is working very well, especially if you have a domain that is very close to regular shaped elements. But we want to push this more to more demanding measures, more unstructured problems. So very recently, we have developed a matrix-free algebraic HP multigrid that is combining P multigrid with then a matrix-free algebraic multigrid method as a full preconditioner. This is showing a great result and is beating HSMG, the additive overlapping Schwartz one, for more industrial problem where you have a lot of curved, long, slender elements that you often end up with when you go for more industrial cases. And if you want to know more about the matrix-free preconditioner, that will be a talk actually at HPC Asia this January covering that development as well. So with that, we sort of have covered the technical part that the new things are getting into Neko 1.0. So the remaining back half of this webinar, I would like to showcase how Neko is used, how to install it, and how it can be used and expanded based on users' need. And throughout the slides will be provided afterwards. And in the slides, there are pointers where you can find more information or also find examples which you can continue to try on if you're interested. So the first thing to install Neko, you don't need that many dependencies. You basically, of course, need a Fortran compiler. And you need auto tools, lib tools, package config, these utilities that you often have laying around on a machine. What can be a bit tricky is that you need an MPI that actually it can do Fortran 2008. An important thing is that you actually have this module MPI F08, which most MPI these days can produce if the compiler is good enough. But there are still some vendors that are not shipping these. And instead of reverting back to old MPI, as was presented at ISC last year, or this year actually, is that the latest MPI standard will deprecate the old way, so this is the way to go. So hopefully this will be resolved soon when vendors are catching up this. Finally, you need BLAS LAPACK, and also you need JSON Fortran. So these are the only sort of core dependencies you need to run Neko. And then to install it manually, if you don't want to use SPAC or Pixie, as we also provide, you just do a normal configure with auto tools. You give a lot of compile options you can do. You can leave the prefix where things are going to be installed. And then you have a long set of options, either features that can be enabled or disabled by doing enable feature, disable feature, or adding optional packages with or without. And what these can be are, for example, compiling in support for writing HDF5 data. That's going to be done with HDF5. You want to compile with CUDA to enable the CUDA backend in Neko, then it's with CUDA. Or for example, if you want to enable a device-aware MPI such that your data is communicated directly from the MPI, that's then enable device MPI. We have too many options here to list in this webinar, but when you have the slides, follow this link on the Neko manual at neko.cfd. There will be a very detailed list of all the options that are currently supported in the release. So a quick note on that before moving on. So when you go to neko.cfd, there are two manuals that you can access. One is the latest release, one is the nightly develop. And since Neko 1.0 is not released yet, until then, always click into the nightly develop, then you get the most up-to-date documentation, which is now actually following the release branch for 1.0 pretty steadily. So some examples how to install it. So for example, if you want to install with CUDA, as I said, you do with CUDA, give path to CUDA. You can set some CUDA flags, the architecture, and then you can enable the device MPI by doing enable device MPI. If you have an AMD GPU machine, similar thing, you can do with HIP. And if you want, you can also change the HIP compiler. You have an MVCC option for CUDA as well, but with HIP-CC, you will say, I want to use, in this case, the Cray C++ compiler to generate my HIP code. And HIP flags have a kind of a different naming, but this is also, again, covered in the manual. And for completeness, if you want to make a CPU build, now in this case, you want to do a single position CPU build, you just configure, you set C flag, Fortran flags, and the keyword here is that to enable single position, you enable real equals SP. So the default here is DP, that would be everything's double precision as default, but whenever real, most of the arrays will be single precision, except reductions and very sensitive arrays, they are still in double precisions. If you so happen to be running on a machine that only supports only single, you can do SSP to actually do a true SP42 build of Neko as well. And again, all this is covered in the manual. So if you're interested in tuning this, please head over there and have a look. So now I'm going to talk a bit about setting up the case. And there's actually one slide missing here, but that's also left out of purpose. Because running a case, you need two things besides a working Neko installation. You need a description of the case, this case file. And secondly, you need a mesh to do the simulation of. So currently, Neko supports meshes generated from Gmesh, which are then converted into NEC 5000. And then NEC 5000 meshes are later converted into a native Neko mesh using Neko's own conversion tools. So this is a bit of a clunky workflow that we are trying to streamline a bit before the 1.0 release. So that's why that slide is omitted in this presentation, but it will be part of the documentation once we get the version out of the door. So instead we focus on the case file, how you define a simulation in Neko. And this is done with a JSON file. And the first one, the version there is just so that we are keeping track of the version of the Neko JSON description that we have. And then you see you set up your case and close it with objects like time, numerics, fluid, scalar, and simulation components. There are a couple of bit more that are covered in the manual. But this is then naturally the time is you define sort of end time of simulation, time stepping options, numerics are the polynomial order, the discretization, and fluid is the big object with a lot of sub-JSON objects defining how the fluid solver is set up, how the fluid problem behave, material properties, etc. Then you can add scalar transport, for example, temperature or other things. It's not limited to one scalar. If you have a single scalar, it's scalars. And if you have more scalar, then it's called scalars. And then each of these expanded block will then be one block per scalar, so that you can set the material properties for each scalar individually as well. And the last part, simulation components, that is a way of adding components into this workflow that is not necessary to run the solver per se. So for example, computing vorticity, lambda 2, doing statistics on the data. So think of it as you have your workflow from the top to the bottom. You do your fluid, you do your scalar, both of them are in place. Then you can add a couple of simulation components that are using that data to get some output out of it. So digging a bit deeper, looking at the case file, this is how the top part would set up for a case. First, you have your mesh file, then you have various IO options, and then this time object, you see you can set your end time, add or enable rather variable time stepping, set your CFL, and the numerics one is just setting your time integration order, the polynomial order, and other various options. So the top part of the file is pretty easy. The messy part, so to say, is the fluid object, where you set things as your material properties. So if you have in the future compressible, this part can be a bit larger, of course. You need to set all these various physical constants. Initial condition, this is a good example on the various ways of doing things. So typically all the blocks in this JSON file have a keyword type. And then depending on the type, you either can just use a value or you need to have a sub-block of more options in the JSON to actually make this work. So if you have a uniform flow, one in the x direction, you just do a value and the vector value, and this would be your initial condition for the flow. Solver blocks, linear solvers for velocity and pressure, follows the same pattern. Depending on the type here, not the type, you can get more sub-options. preconditioner, that's a good example of a subblock coming from the type. And again, if you look at the pressure one, the HSMG, this additive Schwartz one, there you have a lot of parameters. You can create another subblock related to the coarse grid solver in this multi-grid to set a lot of options. So these files can become quite large, but we have tried to set the default values as sane as possible, and the more fine-tuning is left for the more advanced users, or when we have to debug cases that are not working. Last part is the boundary conditions, and the way this works is similar to everything else. You have a type, so the type of the boundary condition, and depending on that type, you have to add a bit more information, for example, a value or some other parameters. The interesting thing from the meshing perspective, how this works is when you mesh in, for example, Gmesh, you are putting IDs on the boundaries, and these are then what is mapping the zone indices when you later run your case with Neko. So if you then put all your inflow phases in the mesh to 1, this will then be used to apply the inflow condition in Neko in the case file there as well. I will not go through the scalar. The scalar looks similar as well. You have your solvers and parameters, but for those things, please go to the manual. That's better written, that can be covered in a short webinar in 1 hour. So, but rather think a bit how you actually running the case. So this can be done in several ways. So if you install Neko, it will, in your installation directory, you will see a libNeko. You will also see a file called Neko. It's actually a binary file. This is a full solver based on libNeko. If you run this through a debugger, you will see that it's actually called Turbo Neko. So that's the internal name for this one. This binary can be used to solve cases where all necessary functionalities exist in the Neko framework. So for example, if you're happy with the uniform inflow, you only need outflow, all these boundary condition, initial conditions are already inside libNeko. You can just use this pre-installed solver directly. And you can just run it by using MPI or srun that Neko and give it the JSON case file, and everything will work. And if you want to see how this looks like, there is what's called a cylinder flow case in the example directory inside the Neko repository. And that link will take you directly there. And you can see that you don't have a binary there. There's no Neko binary. There's only a case file and a mesh. And that means that this can be run with Turbo Neko. So just use the installed one in the installation directory. But of course, for advanced users, you might want to use different boundary conditions. You might want to use different inflow conditions. So you want to have the ability to actually extend Neko. And for that, you need to write a user file. And the user file can then be compiled. It's a normal Fortran file. So the way it works is that in that one, you are writing a couple of functions that are following certain templates inside Neko. So libNeko has a couple of callbacks, and you're basically writing function matching these callbacks, and make Neko will then, together with the user file, create a new binary called Neko, which is outside, it's in the same directory as the user.f90. And this Neko down here contains the callbacks that you had in the user file. So when you're running your program, libNeko will actually call the things that were inside your user file. So for example, an initial condition or your own boundary conditions. And internally, if you do debugging, this is called user Neko, this program that is produced here. It unfortunately has the same name as Neko that is defaultly installed, but that is part of how things has been done here in the past. And for this, there's a Taylor Green Vortex example in the repository that will showcase how this actually the workflow for this. A quick look at how this user file look like. Basically, you have these callbacks, user, percentage, and condition. These are function pointers, and then you just point to your internal function that you have inside this user.f90. So this is the content, the file here in the middle is the content of user.f90. And if you have compiled a user Neko using make Neko, and your JSON file here to the left contains initial condition type user, Neko will then evaluate this initial condition callback in your user file instead of something inside the Neko library itself. Some more way of extending Neko. The user file might not be everything, cannot solve everything, it's just a couple of callbacks. So make Neko can also be used to compile additional Fortran or even CUDA or HIP kernels. These can either be auxiliary function that you call from the user file, or they can actually be used to extend components inside Neko without putting them inside libNeko. So you can, for example, write a new source term or a new wall model. You can inject it into libNeko using makeNeko. And the reason why this would be interesting is, for example, when debugging and testing a new wall model. Instead of fighting and getting it into libNeko and keeping track of the latest developed version, you can debug this and try it out using makeNeko locally. And when it's ready enough, you can just then issue a PR and then send it into the main repository as well. And the final option is that you can actually use libNeko as a spectral element framework and write everything yourself from scratch with function spaces, linear solvers, etc., etc. An illustration of that is the Poisson example in the Neko repository that does everything from scratch, not using any pre-made infrastructure in Neko besides the types that we have there. So all this is Fortran and C. So we have a new thing coming into Neko 1.0, and that is a C API. And this also means that we now have bindings for Julia and Python. And of course, our aim is to get good performance, but we also realize that a lot of workflows are built on Python or Julia. One use case for this could be that you want to, for example, try a new initial condition. You don't want to recompile your Python thing all the time. So you just want to type up a small Python function, and you want Neko to actually evaluate that. And this is how these bindings work. So for Python, we have something called PyNeko, and that's actually part of the distribution. So if you enable Python when you install Neko, you get the PyNeko bindings. Julia, unfortunately, due to how Julia works, we cannot ship it with Neko, but there's a neko.jl package that provides the same interface as PyNeko so that you can extend and run simulations from Julia. But back to the example, if you want to set an initial condition using Python, you can easily define it like this. You can then create a Neko callback inside Python, pass it down when you initialize your case, and when you run it, you can actually single step this in PyNeko. When you run it, what will happen is that Neko, via the API, will actually call your Python code and then evaluate this method or function inside Python to access and set initial conditions. And how it works is that the PyNeko field here will actually get a field from Neko. It will not create a copy from Fortran. It will actually give you a pointer to the underlying data. So when you're doing UXI equals 1 here, it will not be a Python buffer that is later flushed to Neko. It directly modifies the data that was allocated on the Fortran side. And just a quick demo before the wrap up here. The reason why this is interesting is because that allows us also to start working in a more interactive environment, especially for teaching or rapid prototyping. So I prepared a small notebook containing one of the examples we have. So if you just fire it up, we get the normal Neko banner when you start. So warning because this machine is as it is. And then we, in this example, set initial conditions. We want to set it to 1 everywhere in the domain. We also want to create some inflow condition. So here we see that we're extracting UVW, but we only set U to 1. Then we can creating these callbacks by just passing this Python function, initial and inflow, via some wrappers that we have inside PyNeko that will create the correct function pointers. And later on, we can create the PyNeko case like that, and a lot of output will be there. The interesting thing here is that we see from the output that user-defined extensions, initial condition, and Dirichlet boundary condition. These are the same thing you will see if you're actually running on using user Neko with a user.f90 file. So it picks the same code path, so to say. And then in the end, if now the notebook can behave, we then can time step like that. We can take a step. We can actually, if I just move this down, sorry. If we want to look at the field, we can just get the derivative values. We can do another step of the simulation as well. And we can, in between these steps in the simulation, nothing is happening in between. So we can just look at the data, we can plot it if you have good bindings, and then single step this or write a while loop and process the data as we are going. So it's a pretty neat feature that we're adding now in the code. Hopefully that can be used, especially in teaching, or if you have a workflow that needs Python or Julia for the data analysis as well. And with that, we are towards the end. So summary, CFD is one of the great potential to reach exascale. You need good methods. And there you have Neko that is providing a portable framework for high-order spectral element-based simulation of turbulent fluid flows. It has demonstrated excellent performance and scalability across various architecture and hardware. And we are very happy that we are soon getting the version 1.0 soon out the door. The target here is actually to have a third release candidate baked this Friday. And if you now, after this webinar, is a bit interested in trying out Neko, you have the documentation on neko.cfd. There's also discussion forums on GitHub on our repository. And there's also a public Sulep channel that everyone can join without having an account, where you can ask questions with the developers as well. And with that, I'm very happy to take any questions